measure the difference energy with two possible transmit signals. So for binary transmission, there are two possible transmit signals for each bit to be represented. Yeah? And we measure basically the difference energy to the received signal. And then we said at the end, we can map this into our vector notation. Also, the vector is only one-dimensional in this case. And we said we are at the end only interested in the projection of the signal. You can see it here in this figure. Projection of the received signal into our signal space. So we could denote this as decision variation. Based on this single component of our received vector, which is, again, it's only a scalar in this case, yeah, we can make our decision. And then we said for this antipodal transmission, where this is our signal space, if we then use this minimum distance criterion, we can say any vector which points in the positive. What happens here? Which points in the positive direction? Yeah, as can be seen here in this example, is closer to S1, to S1 of t, let's say, compared to S2. So we would assign any vector on the right-hand side to S1 and any S2. This is basically what we see here. So this decision, this minimum distance decoding at the end, which is a maximum likelihood decoding. See it later. It's just, we need just one threshold device, and the threshold is exactly at 0. And you should remember the seminar task, and then we switch to on-off keying, as you remember. And in on-off keying, of course, this threshold is not at 0, because then the signal space looks a little bit different. Yeah, it's basically like a shifted version of this. One vector is just 0. We switch the signal off 0 bit, for instance, and then we switch it on for 1 bit. Then you would have one vector which is just 0, other vector which is just square root of 2EB. So the average energy per bit would be EB. This means that if you transmit a 1, you have twice the energy average bit, about zeros and ones. And now we just want to proceed, and I will show you that we have an alternative implementation of this detector. We can use, instead of the correlator, we can use a so-called matched filter, sampled matched, which has exactly the same performance. Yeah, and so it's basically realization if you do this later, or if but if you implement this as a filter, you can really see what happens in practice. In practice, you basically reduce the noise as much as possible, because we have this additive white Gaussian noise, and you reduce the noise variance as much as possible by keeping the desired signal also as much as possible. So at the end, maximize the so-called signal-to-noise ratio, yeah, at the sampling times. This is what we are doing with this detector. So this matched filter approach provides insights into this problem. Before we come to the matched filter, we just want to say, okay, now we know this is Y1, right? So we do our decision based on Y1. And now let's have a short look. How can we decompose what's within this Y1? That's quite simple. So we can say, if we take a look now at this Y1, let's say I do this in black, yeah, because this is Y1. This is Y1. Now we want to analyze this. And you see what we need to do. We need to integrate from 0 to TB. Why? Because we assumed this one-shot transmission. Yeah. So and we said our signals to be used to represent the bits are for the first not longer than this bit interval. Yeah. So, and since we only consider the bit with index 0 for this first approach, yeah, we say we only have to integrate 0 to TB. So then we say expression, so y of t, correlation with our basis function, integrate over. This is basically what's within this. And then we have to decide based on this y1. This is can be seen here. Maybe it's in black. To see this is our decision. By the way, I don't know if this is a good idea. Maybe I didn't start a new works, so copy to. Oh, it's a new lecture, and you see the out basically. And now we say, how can we decompose this? Because now we can say this received signal is just the transmit signal. We don't know exactly which signal has been transmitted, but we know there are only two possibilities. That's the advantage of digital transmission. So plus the noise n of t. So we build an inner product basically. Then we can say this is 0 to tb, is I of t times our basis function t, and then there is a second component, integral from 0 to tb, and the correlation, because this is a linear, see here, this times c1 t dt. And now the question is this. So this is our signal, yeah, and we multiply the signal with the basis function, integrate. So what is this? Yeah, this is our signal component, signal space. Yeah. So basically, we obtain, if we would have a multi-dimensional signal space, yeah, we obtain with this equation basically the signal vector. But now we only have one component, so we only get this single component signal vector. But this fully describes our signal. So we know this SI1 is alpha plus square root of e minus square root of e. And then we get, let's say, the projection of the noise in our signal space. So we can say this is just a projection of noise, so of this AWGN, yeah, the continuous time noise, but this is the projection of the noise signal space. And this is just the signal component. So this is basically ether plus or minus square root of. So in a more general way, we could say, yeah, that if we later, let's say later, yeah, this is just, sorry, just claim this, yeah, but later we will see that generally, yeah, if we use several correlators, because we have a multidimensional signal space, the most important case for us is two-dimensional case. Then we can talk about quadrature amplitude, and then we have basically the signal vector plus the noise vector. So we see if we wouldn't have noise, the received vector is just equal to the transmit vector. So signal component, basically this is our signal vector. Signal vector. And then it's clear that only the component of the noise which is projected in our signal space is all the other noise components basically do not have any negative effect on the signal. This is what we see. So, and of course, we could say, yeah, this is N1. And now if we measure the second moment of this N1, there was the first task in the seminars. consider this two-dimensional pulse amplitude modulation, yeah? And also this may be a little bit difficult, but we solved the following result if we take a look at the statistics of the noise, yeah? The noise before our detector is continuous time AWGN, so additive white Gaussian noise. This is still additive, yeah, but now in the digital domain. And if we now take a look at the variance, so the expected value of n1 to the square. Why I write n1 as a capital letter? Because I'm looking at expected value. So I consider this as a, therefore I use this capital letter. This component, if we use this unit energy basis functions in our model, yeah, this second moment is equal to n naught by 2. This is strange. This is not really a noise variance as in physics, because if n naught, for instance, is in watt per hertz, yeah, then the variance is also in watt per hertz. Yeah. The reason is simple, because our basis function has a unit energy. So you cannot realize this in practice, but this is advantageously for modeling, in our model. In practice, you can correlate with any signal which has the same shape as psi1. Then you get a scaled version signal, vector component, and a scaled version of the noise. But the signal to noise power ratio is exactly the same as before. Yeah? So you will see this later if we talk about the sampled match. We can replace the correlator, that's the next step. Yeah. We would have more correlations than any correlation by a so-called sampled matched filter. So, and this matched filter means it's matched to the used pulse shape. It's only one single pulse shape from the sign, yeah, of waiting. This is basically a basis function. This is the description of the pulse shape. Let's say it's a rectangular pulse or whatever. Yeah? And we could say the detector looks like this if we do this realization, and we can simply prove that this leads exactly to the same decision variable. So we still have this received signal, so analog signal. Our channel is an analog signal. So we know this is transmit signal plus the noise. And then we say we build a filter, and the impulse response, G of t, of this filter is equal to C1 of TB, because our integration interval is TB, okay, minus T, this is the important thing, this C1 of minus T, this TB just makes a shift, yeah. Pulse. So, and this is the so-called matched filter. It's described by the impulse response, in this case, in the time domain. So this is the matched filter. So it's matched to psi1 of t, to the signal, to the desired signal component. And then we sample it, and therefore it's denoted sampled matched filter. We sampled it after we received the pulse. So we sample it here at t equal to tb. And we have, again, just one decision variable. Let's say this is still our y1. Then we do something with the y1. And again, yeah, since we talk here about this antipodal modulation, threshold, which is exactly at 0. And then we get the estimate of the signal, or the estimate of the signal vector. Doesn't, it's the same information. And if we want to prove this, yeah, let's say we say, why is it exactly the same as our correlator? And we could say, let's say before the sampling is a first step, yeah, we denote the signal, let's say at this point here. Let's say I denote the signal as W of, then we could say this W of t is just an intermediate step, and this is Y of t. We need to do the convolution with the impulse response G of t. Is the convolutional product defined? We could say this is integral from minus infinity to plus infinity, Y of tau times G of t minus tau tau. This is just a convolution. But we are only interested in W of sample. Now we take a look at the sampling time. Because at the end, we have to decide, once we received the signal and processed it with this filter, after this step, we have to decide. Yeah? And so in practice, of course, we receive a sequence of pulses, a long sequence. Yeah? Do not transmit just a single bit. We transmit a sequence of bits. Then we sample, yeah, with every TB, 2 TB, 3 TB, 4 TB, and so on, with every modulation step, of course, yeah, signal. So we will use this later. And now we take a look at just exactly at TB. How does the integral now look like? Now we can just insert TB for this t. So it looks like this. Integral from infinity to Y of tau, of course, G of TB minus tau tau. Now we replace this G of TB minus tau just by this expression. So we say, now we write this as a function of this basis function. This is, of course, the same as integral from infinity Y of tau times. Now I replace this by C1 of. Now this t is replaced by this expression. So we get TB. This is this TB here. Maybe I write this in. See it? Yeah. This is exactly this TB. So now minus, maybe the time is now TB minus tau. D tau. Now you can see, okay, what happens is equal to TB minus TB, 0, and minus minus tau is just tau. So you could say this is the same, and since our basis function, we assume that the basis function for the first is 0 outside the bit interval. Okay? And then we could say, in this case, we can integrate just from 0 to TB because our basis function, yeah, has this length. And then we have here Y of tau times C1 of tau. So at the sampling times, it's exactly the same as this correlator. If you denote this as tau or t, doesn't matter. So you can replace this tau by t if you want. You can call it as you want. This is just a number. How I denote this time variation doesn't matter. So this is exactly what we obtained with the correlator out. It's exactly the same. So we know we can replace the correlator also by a matched filter. So, and it's interesting further to take a look what happens. Let's say just to have a closer look at this matched filter, although we later also come to this matched filter. What happens? Exactly. It's just you have a certain pulse shape. If you have a single dimensional signal space, you have only one dimension. Then you have only one shape that you are using. You may change the amplitude. You have to change the amplitude of this shape, but you use just one single pulse shape. You can say, yeah, in our model, this is the basis function. Yeah. This is a scaled version of this pulse shape. And then I match the filter impulse response exactly to this pulse shape. That's the whole story, basically. It's matched to the basis function. You're right. But in practice, yeah, even this impulse response cannot be realized. We take a look later. We take a look on this, yeah, because it has unit energy. It's impossible to realize this, yeah. At the end, you will see it now, yeah. We get the signal component at the output is a square root of an energy. So in practice, you can detect a voltage, but not a square root of an energy. Yeah? This is just a model. You can scale it, and then everything is fine. You can have any practical filter has basically a scaled version of this impulse response. The shape is the important. Now let's say what happens, let's say, if so we switch off the noise for the first. Exactly. Or I do it maybe I do it in this way. A closer look. It's a little here in my script, yeah. Let's say I take a look at this Y1, basically, at this W of t. So I can come again to this W of t, and this W of t is basically exactly. So we said it's the same as if we say this is our signal component. So this is basically our signal. Yeah, this is I of, as you can see, yeah, this I of t is just our basis function, but with a weighting square root of EB, square root of EB, nothing else. Yeah, then plus the noise n of t. Then we could say now we do the convolution because our impulse response is just C1 of TB T. It's exactly the same. So, and then what do we get? We do this convolution SI1, C1 of T, with C1 of minus T. Do you know what this is? Do you remember what is psi1 of t and then the convolution with psi1 of minus t? What was it? What? Sorry? It's the autocorrelation. This is just a shifted version of the autocorrelation function. So what we get at the output of this matched filter before sampling, if we take a look at the signal component only, yeah, we get a shifted version of the autocorrelation function. So, and this makes sense because if you take a look at the autocorrelation function at tau equal to 0, you can see the energy. So you could, if you want to have an idea what happens, you could say the matched filter, yeah, basically focuses the energy of the received signal component at the sampling time. This is what happens. So you could say this is just phi C1, C1. And now we cannot write just of tau because we see this really output of this filter of t, but it's shifted to the right. Yeah? Because we have causal, assumed a causal filter here. This is the weighted version just of this auto. So, and since we use a unit energy pulse at the sampling time, our autocorrelation function is just 1. So this is just 1 at 2t, because this is the autocorrelation function at 0. Since we assumed unit energy, psi1 has unit energy, the energy is just 1. So, and then this is just basically, we could say plus minus square root of. And we know the signal component, if we take a look at the signal vector, yeah, the signal component is either square root of v minus square root of. So you see the difference between y, the vector y, the received vector, transmit signal is basically the noise vector. So you could interpret this, maybe I write this in this figure, yeah? If I transmitted S1 for this received vector, the noise vector would have been this one. Yeah, I just draw it here. There is one possible noise vector. If S1 has been transmitted, yeah, this would be the corresponding noise vector. So the mapping of the noise into our signal space. But if S2 has been transmitted, which is possible, yeah, then the noise vector would have been this vector. And you can see this noise vector, yeah, is longer, but if we have a Gaussian distributed noise, higher noise amplitude are less probable than lower noise amplitude. So it's more likely that this lower noise appeared in practice than this higher noise amplitude. This is really important, yeah, to see this, what happens. And we have to say, okay, we have to finish this expression because now we also have to take a look at noise component. So this is basically n of t plus n of t. Then we have to solution with this impulse response of the filter, so with C1 t. So this is what we denote as N1. So and now, so we see we have the vector the signal vector component. This is either square plus or minus square root of. And it looks like this function looks like the autocorrelation function. The sampling time is just our vector component as before. Now we can analyze the noise and we can prove much simpler than in this seminar. Phi is the second moment of this noise component and not by 2. Yeah? Because now we could say the expected value noise component of N1. So again, I write N1 as a capital letter, not because it's frequency domain or whatever, because I say, yeah, oh, sorry, I wrote this correctly. It's correct, yeah. Because it's a random variable. And then we are interested in the noise power, and we know, yeah, the noise power can be calculated. So we have additive white Gaussian noise, okay? Additive white Gaussian noise with a power spectral density and not by 2. This is the input noise power spectral density. Then we have a filter transfer function, which is G of f. Yeah? But the noise power at the output of this filter is not by 2 times G of f magnitude squared. So this is the noise power spectral density at the output after this filter. Then we have to integrate, yeah, the noise power from minus infinity to plus infinity to get the total noise. This is basically the autocorrelation function, yeah, this value of the filtered noise at the output at tau equal to 0, which is the same as the second moment. So df. Now if we insert this in our special case, so we have white noise, we can put this and not by this integral. Then we can say this is integral from 0, from minus infinity to plus infinity. We simply have squared. And what is it? This is the same as is equal to n naught by 2. It's integral from minus infinity to plus infinity. Now look, the impulse response is C1 of Tb minus T. So the transfer function is basically, if we would say G of T is C1 of minus T, then it would be G of f complex conjugated. But this doesn't matter, this complex conjugated, because we are only interested in the magnitude squared. So we could say in the time shift only, changes the phase in the frequency domain. So all of these things have no impact. So we could say this is the same as this. It's exactly the same. So, and what is it? This is the energy of the signal. And the energy can be measured in the frequency domain, in the time domain. So this is just 1, because we assume this unit energy. This is n. This is n naught by 2. So we see in our special case, the noise variance, and you see it in practice, this will not appear, but we talk about this later. This is a good model to calculate something. If you want to realize something, yeah, and you have a filter, if your signal bandwidth increases, so if the bit interval decreases, you transmit at a higher bit rate, you increase the bandwidth of a real-world filter, and you get more noise. Here you say, I normalize this filter in order to have unit energy, yeah, and the noise variance is independent on the bandwidth of the signal because of a normalization. But at the end, we will see we get exactly the same. Now we are able, now we have the noise statistic. We know the signal values are either square root of e minus square root of in our model. In practice, it may be 1 volt or minus 1 volt. It's square root of 1 watt second minus square root of 1 watt second. Strange, but it fits to our model. You can calculate the bit error. So and this is basically 5.3 bit error rate, bit error ratio. This is abbreviation BE. And we talked about this before because I introduced this complementary error function before. Yeah, we need basically we need the statistics, and we have it. Yeah, statistics of y1 if S1 of t, and I write or S1. Yeah, doesn't matter what we write. The signal or the signal vector has been transmitted. And if S2 t, S2 S vector has been transmitted. Well, we transmit an analog signal, of course, transmitted. Then we know the statistics, so we need to know the conditional probability density functions. And now we can draw the conditional probability density functions because we know this is quite simple, yeah. The expected value of, let's write this like this, I think you can understand this. The expected value of y1 if under the condition that S1 of t has been transmitted. This is just square root of e, because the noise is zero mean. We have zero mean noise, so we average, yeah, over this, yeah, see it here. Signal component plus noise component, but noise, even the filtered noise, is zero mean. Expected value of the noise, not a square. This is just zero, and the expected value of this decision variable y1 if S2 has been transmitted to this assignment is just minus square root of. You also know, yeah, that everything is linear, yeah. Data is linear, filter is linear. So the variance of this noise, this is n0 by 2 in our model again. So, and then we could say, okay, how does it look like? Probability density function, let's say if S1 has been transmitted, it's like this. So let's say if we transmit S1, without noise, we get exactly square root of e. So if there wouldn't be noise, let's say I write here, if there wouldn't be noise, yeah, and I know S1 has been transmitted, there is a direct delta pulse because if I draw the probability density function, because then it's for sure, yeah, get always the value square root of. But with noise, the noise is Gaussian distributed. We know variance of this noise. So we can draw here a Gaussian distribution, which may look like this. Yeah. So this is a Gaussian distribution. We could say this figure is just f probability density function. It's a conditional probability density function. Random variable S1 depends on signal vector. So, and now I use this shorter version for the notation. Yeah? Usually you would write here Si of t, here O. Yeah? And this is the amplitude under the condition that I is S1. I just write here S1, yeah, to say S1 has been transmitted and I'm interested in the amplitudes. Yeah? It's a probability density function, the conditional probability density function if of y1, yeah, or one of our decision variables, if S1 has been transmitted. X is, of course, this is the amplitude. This is looks like this. Then we know if we want to just describe this, the width of this curve, we know we describe this by the standard derivation. The square of the standard derivation, yeah, this is just the variance. In our case, this variance, yeah, since we have here square root of EB and not a voltage, in practice, you may. The noise power is also, yeah, in volt squared. But here we have square root of EB, and therefore this is also still a power spectral density. Yeah? So everything is fine. Yeah? And then in the other case, yeah, 6, 3, 6. If I transmit the second signal, so let's say a binary 0, yeah? So without noise, I would always get square root of minus square root of E. But then I have to consider the noise, and sometimes I receive more. Sometimes I receive less. It's like this somehow. It should be a Gaussian distribution. It doesn't look nice. So simple. Here. Then this would be basically if S2 has been transmitted. So again, a condition density function. Then you can immediately see, yeah, you can prove this. We don't do it, yeah, as you can see it basically. The optimum threshold is exactly here, 0. So where we have to decide if y1 is larger than 0, then probably S1 has been transmitted. If y1, we take a look at the statistics of y1, is lower than 0, then probably S2 has been transmitted. Because now the probability of an error, so any amplitude x on the right-hand side of y1, yeah, this is the actual amplitude on the right-hand side is said to belong to S1. So, and this means if S1 has been transmitted, yeah, and we receive an amplitude lower than 0, get a transmission error, bit error. So this would be basically, so this area here is basically the probability that a transmitted 1 is wrongly detected as a 0. And on the right-hand side, if we take a look at this area, let's say, this is the probability that a transmitted 0 is received as a 1. But if we would shift this threshold for the decision to a different value, we would heavily increase the bit error rate. See, this is the best case. Can simply prove. And again, remember our noise vector, yeah, larger noise vector, the lower probability vector, vector with a lower length. Remember this figure. So we would choose S1 for this case, because in this case, the noise vector would be shorter than in this case. This is just comes from statistics. If we wouldn't have this Gaussian distributed noise, yeah? This wouldn't be as simple as in this case, but now it's clear. And now we can calculate the bit error, and we can write the bit. Let's say we have the optimum threshold, yeah? Integrate from 0 to infinity. It's exactly this area. This green area is the same. And just insert the probability density function. So this red one, maybe I insert this red one, 1 by square root 2 pi, and then the noise variance, and this noise variance is n2 in our case. And then we insert this distribution, whereas the center at minus square root of e. So this would be minus x plus square root of e, yeah, divided by 2 times the noise variance, as you remember, square dx. So, and if we simplify this, we have done this before, you can check it. We introduced the conjugation before. Yeah. So of course we can here in this expression, we could say this cancels out this and this cancels out. Yeah. Then the basic approach is to make a substitution. Yeah. But I don't show the whole story because it's also done in the seminar, and we have done x plus by n square. So this is what you can see here. Or z is equal to x plus square root of by square root of n. Substitution, yeah, and say dz to the derivative of z with respect to x is 1 by square root of. Then we get the following integral at the end. If we substitute everything, we get the integral square root of e by n. Due to this substitution of the integration variable, so we have to integrate that to infinity, 1 by square root of I to the power of minus z squared z. So this is what we get. Then we can say this can be written as the complementary error function, yeah, because this is nothing else than this 1 by square root of e belongs to this complementary error function, yeah. So with maybe here with half c is equal to 2 by square root of the square root of integral from to x t, here's this x to the power of z squared z, yeah, and we insert this and we get that the result this is just 1/2 c square root of c. Bit error rate, this is an important result, only depends on the ratio of the energy per bit to the noise power spectral density. This is really important, this result. E by n naught is also referred to as bit referred signal to noise ratio. So it's related to the bit, yeah? Bit referred signal to noise ratio. To power ratio, or just simply the E by n naught rate. See it in any book, yeah? Take a look at the axis of the figures. This is EP by signal to noise power ratio. Signal power ratio. Also use this Q function, but here we use this function. Then we take a look at the slides. We can see how it look like this complement. Then we make a example which can also be seen on slides. Example. So if we say we have thermal noise, then the power spectral density, best case is basically, I mentioned this example before, it's Boltzmann's constant times the absolute temperature. Let's say T is 300 temperature. It's just a temperature. I want to make it short, this example. So, and this is Boltzmann's constant. And then you could say, if I take a look at this, and let's say I denote the required. So we require a certain EB by a naught ratio for a certain bit error rate. Here we have the bit error rate. This is PB, the bit error rate. Maybe I write it here again. This is the bit for a certain bit error rate. Let's say 10 to the minus of 12 or 10 to the minus of 3 if you use forward error correction. You need a certain EB by a naught ratio, and we denote this required by an ratio a certain R E. So we want to ensure a certain bit error rate. Then we have to ensure, for instance, EB by a naught is 10. Then we denote this as eta, let's say, in the linear, not in the. So this ratio, we just want to say this is eta. Yeah? Then we say, okay, therefore, the required energy per bit, yeah, is just this required ratio times our actual noise power spectral density. So this is, we need this energy per bit, okay? Given, so we have a real world noise power spectral density, which is Kb plus T. Then we could say, yeah, we can replace this EB. EB is the same as the mean power signal, say where the noise appears at 0. Yeah. So we said we have no attenuation. Yeah. So this is the noise, the signal power times the bit interval times, so this is EB, mean power times the bit interval times this required signal to noise ratio, this required EB by times N naught. So and now you can see, yeah. Sorry, what the heck? Sorry. This is equal to expression. This would be the times the temperature, and therefore, see the required power L signal power scale in watt. Yeah, P is equal to the required signal to noise power rate times reciprocal value of interval, which is the bit rate. Remember, R is just the reciprocal value, is the bit rate, times T. And now we can fill this with numbers. We can say, okay, Boltzmann constant, this is constant. Temperature is, for instance, 300 degrees. We could say, now we insert a certain bit rate, and you see, if I linearly increase the bit rate, I have to increase the signal power also in the same linear scale. So if I want to transmit instead with 1 megabit per second, with 1 gigabit per second, if I have the bandwidth, I need 1,000 times more power, because I need to ensure the same energy per bit. And if my bits are 1,000 times shorter than before, to have the same energy, I have to increase the power of these pulses by a factor of. This is the real world. We are interested in powers. Now we can take a look at, so let's say, if I hope this is still correct, see slide 17. See it, this is not correct. Slide C. So this is our filter detector. Seeing this graph, the conditional probability. EB by inserted these values, and the only thing changed here is, look, express the power in decibel scale. I refer, I cannot simply say if I have a power of, let's say, 1 watt, yeah, simply take to normalize this power by reference power. Often you use as a reference power. This means if your required power, watt, I refer this power to 1 milliwatt, I get 1. Look, oh, it's just 0. So this would be 0 dB. So 0 dBm, you need 1 milliwatt. If you need minus 30 dBm, you need 1,000, still part of 1,000, yeah, of 1 milliwatt. This is minus 30 dB. Now I insert noise for this thermal noise at the temperature of, so nearly. Here you can see first a bit on EBI or not, but also on in dB. So I take the 10th logarithm, this ratio, and multiply 10 because it's a power ratio and not a ratio. So, and you can see, for instance, for a bit error probability of 12, I would require near ratio of 14. If I'm only interested, let's say, in a bit error probability of 3, then it's less than 7. It's a huge difference. 7 dB, 6 dB is a factor of 4, so it's more than factor. Any practical implementations of these forward error correction schemes, even if you do hard decision, yeah. For instance, if you use Reed-Solomon codes and you add only 7% redundancy, so you have to increase, yeah, your bit rate by 7% compared to transmission, and then you aim to switch from a bit of 10 to the 3. This is the gain you can obtain with forward error. Now look, this was not. Switch to the next slide. This is the required power, this Y scale. So here we have the bit. I used here 3 desired. One is 10 to the minus of 3. Then you in the find this with forward error, of course. Yeah. In this case, statistically, 1 of thousands would be statistically. So, and then, yeah, if you have a bit rate which is here measured in megabit per second at room temperature, and if the bit is just 1 megabit per second, best case, get a receiver sensitivity which is 107 dBm. Lower this value is, the less the power is. But if you need a better bit error probability, let's say 10 to the minus of 12, yeah, you see this difference of nearly 70 dB. So I mentioned before. Then this eta is higher. So, and then if I increase the bit rate more and more, let's say I'm interested in 1 gigabit per second. 1 gigabit per second. If I have bandwidth, I use this modulation scheme, then in the best case, my receiver sensitivity, yeah, is let's say minus 77 dB. It's a difference of a factor of 1,000. If I increase the data rate by a factor of 1,000, yeah, I have to increase in the linear scale the required power also by a factor of 1,000. Remember, we need to have the same energy in much shorter pulses. This means in dB, 10 times log 10 of 1,000 is just, this is 30 dB less good, this value. See this 30 dB. Okay, that's nice. Again, we make a short break and 5 minutes. Then I want to close it fast. Let's think. 46, okay. So, okay, welcome back. The next subsection is basically matched filter, more detailed. But one part of this section is basically the derivation that the matched filter maximizes the signal-to-noise ratio sampling time. I don't want to do this derivation here on my note. Just showed on the slides. The derivation is not so complicated, as you can see. Just want to prove that this ratio, this signal-to-noise ratio, we said this is EB by a knot, as you remember. Let's say it's basically, it's a little bit different. Say we measure the signal power at sampling time, power so at the sampling time. Say it's like this. It's at the highest signal-to-noise ratio. So you see here the sample signal amplitude at time 0, y0. Now I assume a special case. I assume here for this figure, maybe you can use that this impulse response is just my C1 of minus t. So I skip this TB minus t. So this would mean the output here of this filter would look exactly the signal component as the autocorrelation function of the signal and not the shifted version. Why I do this? Because for the first, this derivation is simpler. Second, later we will see we can use signals for modulation which are longer than this modulation interval. And in our modeling, we could even say these signals have an infinite duration. So this P1, the basis functions. Maybe these basis functions are sinc pausers in the time domain. So they have infinite length. And then I need to develop a filter which is matched to the sinc functions. And I cannot make this filter impulse response causal because the sinc function is infinite length in both directions. So there is no causal filter. The way there is no real world match, it's just a limit which we can obtain for transmission. Let's see. So I assume the only difference compared to this G of t is just C1 of minus t. So now to investigate why does this filter basically ensures the highest signal-to-noise power ratio. So, and now I just do one basically assumption. I simply assume this, because we match this to the basis function, that the impulse response of this filter has unit energy. And if it has unit energy, at the second moment of the noise at the output is just equal to our noise power spectral density. So we describe this noise by the noise power spectral density. Since we said the power spectral density at the output is then n by 2 times g of f squared, integrate this, to get this and not by this is for sure. The only thing to be proven is in this case, then the signal power should be as high as possible. So what we basically do, I basically show the result to you, is obtain is the following. It's this. If we take a look at the picture, this is if we use this matched filter, say we this continuous density functions. So we assumed a filter, even if it wouldn't be a matched filter, is unit impulse response. So this means the noise power is always the same. So and this means the standard deviation, this probability density functions is always the same because there is this noise component. This is a not by So they always have the same. But if we switch from a matched filter, other filter, it's not a match to our impulse, to this pulse shape, then we decrease the signal components and therefore the signal power at the sampling time. This would be here the dashed lines. Yeah? So we have the same noise variance, but the density functions become close to each other. And then if we take a look at the bit error rate, in this case, matched filter, we only have this area, small area. If the become closer together because we use the wrong filter, yeah, this area is much larger. This dashed curve. Derivation. It's shown here. Basically use this Cauchy-Schwarz inequality. By the way, here I assume that we C1. I just say signal S1. Sorry, yeah, everything is correct. So I say we transmit S1 of T. We transmit S1. Either S1 or minus S1. S1 is S2. Is antipulsar transmission. Yeah, plus minus S1. Sorry, it's wrong. So now I switch to without a mouse here. So we transmit this. What do we do? So we transmit S1, and we know already the noise variance is N0 by 2. So we focus our attention to the signal component, the signal power, and not to the noise power. That's the only assumption we are to normalize the filter that it has unit assumption. But we are interested in the shape of this pulse. So this is S1 of t with G of t, and I said, yeah, just assume a non-causal version of this filter. So we say this G of t is nothing else in the time domain as psi1 of minus t. Then if we want to calculate this here, interested in the sample t equal to 0, so sampled matched filter. But we can express this in the frequency domain because a value of a signal in the time domain at t equal to 0 is equal to the area, yeah, area of the frequency domain description. So if I multiply S1 of with G of f, get this what I call WT time domain, W of f in the frequency domain. But if I'm interested in W of t equal to 0, this is just the area frequency domain. So I have to integrate from minus infinity to plus infinity, S1 of t times G of f, S1 of f times G of f, yeah, and there are two possibilities for this S1 of t, namely plus 1s, 1s of t. This is the expression. And now, yeah, we say we can express this S1 of f as psi1 of f times plus or minus square root of v, as we have done before. Then we get basically, if we take a look now at the square of this amplitude, the sampling time, because we are interested in the signal to noise power ratio. The noise power is known and not to variance. Now we want to square this value. So this is 1f squared. This becomes EB. Then we have to square this integral. And you see, we end up with this expression 3. Expression 3, yeah, we have this lower this expression, and this is Cauchy-Schwarz inequality. This equal sign is only possible if basically this G of f has the same shape as psi1 of f. Otherwise, you always have this sign. So we know the signal power is in the best case equal to EB. Why is it EB? Because we assumed unit energy for the filter. This was the only assumption. But only if this shape of this G of f is equal to psi1 of f, we can use this equal sign. So this means in the frequency domain, so if we go in the frequency domain, we know this G of f needs to be, I said psi1 of f needs to be the complex conjugate psi1 of f. And therefore, in the time domain, there's only one possible solution, that the equal sign holds. In this case, G of t, the response, needs to be psi1 of t. Again, this is just the non-causal, the anti-causal version of our data. We cannot realize this in practice because we cannot realize a filter which is not causal. Yeah? So the impulse response begins before t equal to 0, before sightless filter. But from method, we want to simplify this. Yeah. So this means this is a optimal solution, maximum signal to noise power ratio. In this definition, as the ratio of the signal power to the noise power, okay, then it would be by not by 2. In the previous equation, yeah, don't misleading, yeah, I said eta, yeah, is EB by a not ratio. See, it's EB. So the signal to noise power ratio at the sampling time is indeed EB by 2. So our noise power would be N. But this is just a simple scaling. But what is important for you, yeah, if you follow this, let's say, this, derivation, you can see, yeah, for a given noise variance, independently if this is a not or 2, yeah, or any other value, only the matched filter to the highest separation, basically, of 2, because the focuses the energy of the signal at the sampling time. This is the basic idea. Sample now, because this is switch back, say, okay, let's provide examples where we see the difference because between the version and the non. See later, we need the non-commercial version as well. Some derivations and the average, it's the signal power if we transmit a 1 bit, so if we transmit a 0. Bandwidth. Inge? Average, it's the average energy per bit. So, of course, if you transmit, if you use on off gain, so yeah, basically still separate the, say, the distance between the density functions, yeah, which is in our case the U distance between the signal vectors is exactly the same because of polarization, yeah. But the center for an off gain of this one distribution is 0. The center is square root of. We transmit a pulse. If we don't transmit a pulse, we don't have a signal power. If we transmit a pulse shape is described by this psi1 of t. If we transmit a scaled version of this pulse, then we always get the largest possible signal power. So now, other questions and discuss this. Just want to provide some examples, let's say. I've filtered more details, yeah. But you have to know, yeah, this filter ensures the best signal to noise power ratio for a given received pulse. You have to know the pulse to be received, this shape, match the filter impulse response for this pulse. So it's and now filter. Details, yeah, just some more things. Say, consider an example. The following signal. This looks like signal here. Saying the signal looks. See again in this example, the signal is not long. Here in understand this is S1 of t. So we would transmit S1 of S1 of t, dipole transmission. So and this would be, let's say, U naught. Yeah, this is minus U naught. So we transmit S1 of t minus S1 of t. Pulse response. Now we can distinguish because between let's say a causal version a filter and causal version, or in this case of the impulse response. So non. Then we could say, if we want to have for this pulse shape a causal version of the impulse response, yeah, we could say g of t is equal to, and now I don't need this psi1 of t. I just say, yeah, I want to have a filter and the impulse response is matched to this pulse shape. This is also a scaled version of the basis function. And I say the impulse response then for a causal version is g of minus t, but look, g of minus t would be just this pulse on just mirrored to the left-hand side. In order to shift it to the right side back, I need to write tb minus t. Because now the length of our pulse is tb. If this pulse would be longer, let's say 3 tb, yeah, I need to write here 3 tb if it would be longer to make it causal, yeah. And then, S1. Yeah? And then I need to scale this by a certain factor, yeah, in order to ensure a desired design goal. Say this is just a real value constant. So k, let's say k is larger than 0 and real value. It's a real valued positive constant. And we can ensure with this k, for instance, unit energy. But we can also ensure a more real-world implementation where the transfer function of this filter in the frequency domain is unitless, as it is the case in the practical case. Yeah? And here for the non-causal version, we just say the optimum sampling time would be now at TP. Optimum sampling time just at 0. So this makes the modeling much easier to use these non-causal versions. Because here I would say g of t, yeah, it depends on how do we want to model this. Yeah? Of course, non-causal is not realizable. Say there is again such a constant, yeah, times S1, but then you skip this time shifting of minus t. Then you could say, okay, what happens now? How does it look like on the right-hand side? Just say pulse response. Yeah. It's now like this, and we write this, just write this k for the first, and then we further can distinguish. So now I write this version. So it's S1 of minus t. So I switch this from t to minus t. How does it look like? It looks like this. This is S1 of minus t. So this is with an impulse response which cannot really be realized. Why? If this is the impulse response, g of t, yeah, the filter responses to a direct delta pulse at t equal to 0 before I excite the filter. This is impossible. But as I said, it's good for modeling. It simplifies the things. So it looks like this. So, and then we could write here, if this is u naught, we could simply write here, this is k times u naught. We have to find the correct k. This would be k times u naught. But let's discuss this later. So this would be the impulse response. And in this case, the impulse response would be look like this, but we shift this to the right. Then we have the causal version of this filter. Non-causal version, yeah. Non-causal means that your impulse response starts before. This is non-causal. Minus S1 of t. No, so, okay, yeah. Right, yeah, of course. Yeah, it looks different because you have to take a look at the convolutional integral. And it's not S1 of t, of course. Yeah, it's S1 of minus t. In our case, it's the same as minus S1 of t. You're right. But this is the correct impulse response. You have to mirror the pulse shape. So what was here is then here. This has nothing, this doesn't come with this effect you are describing. It's not that in the general case, the impulse response is, let's say, minus S1 of t. The reason it's S1 of minus t. 1 of minus t, if I shift this by Tp, it looks like this. This is the reason. Yeah. So I can provide an example where you understand this, yeah, but then we delete this, okay? So if I draw the same figure here basically, and I shift the pulse to the right, time t, then I shift it to the right by Tb. So this is minus Tb. Of course. Shift this to the right, Tb, this pulse. But this is correct. It's the correct impulse response. But you are right, it looks like minus S1 of t. This is not the general case. Yeah, this is just because of the symmetry of our signal we have. This is Tb. The impulse response is causal. Here we would have k times u naught and k times u naught, say. So, and this would be impulse response in the causal case. Yeah. Now we can discuss about practical values. Let's say is k. So practical values of k, then of k. Let's come back to your example. Let's say you have an impulse response which looks like this. Could be, yeah. It's a strange example, but let's say it looks like this. This is Tb. This is T. This is S1 of t. Just as an example. No one would use this for modulation. But let's say it looks like this. And then if I just write here S1 of minus t, it looks like this. This is S1 of t. Now if I shift this S1 of minus t by Tb, it's like this. So this would be S1 of Tb minus t. This is, don't have this factor k, this is the shape of the impulse response of the It's not S1 of t with a minus sign. It's S1 of minus t. This is the main content. STP to make. See, it's not minus S1 of t. So this was a different example. Yeah, if you want to down, it's fine. Yeah, just for modulation, let's say. Yeah. So now practical values of k. We would say a in order to ensure energy. This means integral from infinity to plus infinity g squared of t dt, even if it wouldn't be restricted to this time interval, is equal to 1. Just want to say the energy of the impulse response is 1. Then how would it look like? Yeah, then we could say we just calculate this k, but we can basically draw again this impulse response. Yeah. Then we could draw a figure. How does our output signal looks like if we transmit S1 of t? If we transmit minus S1, it's a negative version. Let's say we do this. Yeah. Again, I write here g of t. It's exactly what we like this. But in order to ensure unit energy, yeah, I choose a k, which ensures this unit energy, but I don't have to calculate a lot because I know if I write here 1 by square root of t, this is unit energy. Because now if I measure g squared of t is either 0 or 1 by tb. And if I integrate over time, in the actual case, I get 1. So this k, yeah, would be in the example just 1 by u naught times 1 by square root of t. But you don't have to calculate a k. Understand? If the question is you want to ensure unit energy, because then you know the second moment of phase would be a not 2, then this would be the solution. Then how would our signal at the output of this filter look like? When we say, just say, for as a figure, let's say in our modeling, we say we transmit plus minus S1 of t. So we know what happens with the noise. Then we have here this g of t. Let's say I denote the output signal as w of t. Just the output signal of this filter before sampling. So now let's have a look at this w of t. How does it look like? This w of t. This is the causal version of this filter. So now I have to do the convolution of this and this. So we know, yeah, this w of t, also S1 has been sent. And it's, yeah, to know what is w of t, and this is S1 of t, to do the convolution, g of t. To do the convolution, you remember, if we take a look at this convolution, to flip this again to the left-hand side, because this integral, I just write it, yeah, but don't want to spend too long time. But here you see this is integral from minus infinity to plus infinity, S1 of tau. And now look, times g of t minus tau, d tau. So we have to flip it again to calculate this for all the times. So, and since this is the causal version, yeah, it's like this. So up to here, we have nothing. Because we excite this filter with a causal impulse response with a pulse, which looks like this. So, and then we get this. And then we know the response cannot be longer than the sum of signals. So now it's a little bit longer. So, and if I take a look exactly at the time TB, I get the highest value. Basically, here function at this value. Let's say this value. And then, yeah, because of this normalization, let's say I've flipped this, yeah, I mirror this on this x, and then I shift it again back to the right. It looks like this pulse. Looks like the original pulse. So the pulse amplitude was u naught. Okay, then this amplitude is 1 by TB, by square root of TB, and then I integrate over the time, so it's u naught times 1 by square root of TB times TB. And what is it? It's square root of it's the energy of our pulse, right? We denoted this as so. And if we transmit the negative signal, we get this negative amplitude. And then if I shift the impulse response not by TB, if shifted by TB by 2, I get half of this value, of course. Yeah. So basically here, I get a figure of the impulse response, of the autocorrelation function, sorry, of this pulse shape. Yeah. Would look from the shape point of view like this. Since I normalize the filter in a way that it's unit energy, I get, if I transmit S1 of t, I get this, yeah? So S1 of t has been sent, I get this. And here sample, this is the sampling time. This time would get square root of EB. And if I transmit, basically, let's say I do it in red, yeah, or if S2 of t has sent, yeah, then it looks like this. A little bit larger than this and this. We sample here, then we get minus square root of. If we sample here, this is the sampling time, best sampling time, because here we focus the energy. And of course, if we take a look at the real world, this was the real world implementation. If we take a look for this non-causal version, the only difference is, it's quite simple, is then the optimum sampling time is at t equal to 0. It's the only difference. I don't have to draw it again because you know they differ only in the time shift, two impulse responses. Yeah, and this is W of t, let's say. Again, I draw W of t, but in this case, you simply receive this. Exactly the same, but optimum sampling time is now at t 0. Sometimes this is very advantageously because you don't have to think about the length of this pulse. You simply know you have to sample at t of the pulse. If I know the pulse has a length of TB, then it's quite simple to obtain this causal version. But if I don't know the length exactly, or if the length is infinite, so this would be TB, this is 2 TB, and then it's TB minus TB. Now this optimum sampling time is here. So we get either this amplitude or this amplitude. This amplitude, if we transmit S1 of t, and in this case, if we transmit minus S1, this would be S1 of. And we get this amplitude sample at the. This is the only difference. Now we set practical values of k in order to ensure unit energy, yeah. And let's say we choose a k, yeah. But I don't only do the example for the code, just shift it. Say we want to ensure the correct unit Correct means if we want to realize this in practice, yeah, of T G of, then the impulse response in the real world is a unit. It's measured in hertz. Transfer function is unitless. You don't change the units of your signal due to filtering. Same units. Then I just make an example, yeah, for a real world, say, implementation. It's causal, yeah, but it's not unit energy, of course. Say we do this. Then I just draw here the impulse response, G of t. Looks as before, of course. It's so yeah. Then we write here TB, it's T, yeah. Let's say I know the correct unit needs to be measured in hertz if it's an impulse response. Let's say I just 1 by TB, this is minus 1 by TB. Would this give useful result? So now think, this W of t, I write it again. W of t is just either it's 1 of t, and we need to do the convolution with G of t. Okay. But now we get a different output unit. Say our input signal is in volt. This is our input signal. It's measured in volt. And the output signal is still in volt. This is the thing. So of course we know the shape. We just have to take a look at the output. There is no change in the shape. We just scale this k. So we choose a different k. By the way, also you don't have to calculate this k, but this k would be, this example, 1 by u naught, 1 by, to get this response. But now let's have a look, how does it look like? So I start with the orange. One looks at TB. This is TB, this is 2 TB, this is T. So let's say the shape is exactly the same. It's this, yeah, this, and this. So we transmitted S1 in this case. Now let's calculate this value. How large is this value? How large is it? It's quite simple. Again, we think about how does it work, this convolutional product. How do we have to calculate this? So we say we have S1 of t, it's the integral, S1 of tau times G of t minus tau d tau. Now we flip this G of tau, shift it to the right, then it looks like our signal at TB, exactly as our signal, exactly at the time TB. Then our signal has the amplitude. Our impulse response, look in this integral. G of t has the unit 1 per second. Then I integrate over the time. This is TB. And you see, this is a useful output amplitude of a filter. If a voltage comes in, a voltage comes out. Understand? There's not a square root of an energy in the real voltage comes in, a voltage, everything is fine. So it's U naught, and of course, if we would transmit the negative pulse, then really we would have this, say, it would look like this. So, and then this is minus U naught. In one case, it's U naught, in the other case, it's minus U naught. Still focus energy, yeah, but we get real value, real world amplitude. So this would be W of t. Now, is the signal to noise ratio still the same? SNR. So we know S, we know F W of TB to the square. What is it? It's U naught squared, right? If we look here at TB, we take a look at this TB, we only consider the signal component. Desired signal component. Okay, and now we take a look at the noise. Now we have this real-world filter, and we want to investigate the noise at the output of this filter. But noise variance, so this is the signal component, desired signal, noise. So, and we want to find the noise variance, and what do we have to do? We have to say the following. Let's say we denote this noise as at N1, and we know this is, this N1 of T is just N of T, so our noise, and we have to distribution with G1, and this would be filtered noise component. How can we obtain the power? The noise power spectral density is N naught by 2. We multiply with G of amplitude squared, right? Noise power spectral density at the output. We integrate over all frequencies from minus infinity to plus infinity and get the noise power. So this would be the expected value to the sampling time, to any time, square. But now you see, then we need to calculate this G of F. But according to Parseval's theorem, we could say this is the same because this is a constant, and we could also integrate squared of t dt, because sometimes this is easier to calculate. Instead of integrating in the frequency domain, I can integrate the impulse response in the time domain. What comes out? This is, in our case, this is N naught by 2. Look, this is our impulse response, 1 by TB, right? So we square 1 by TB by T squared. Then we integrate our impulse response. It looks like this. Okay. Then what comes out? N naught by 2. This is a noise power spectral density times 1 by TB. Is this correct? Yes. 1 by TB is in 1 by second. So it's in hertz. Watt per hertz, if it would be real world, watt per hertz times hertz. It's what? If it's system theoretic noise power spectral density, volts squared per hertz times hertz, volts squared. Everything is fine. This is a real world variance, noise power. And you see, in the real world, if you have really a real world implementation of such a filter, you could see the noise power increases linearly with the bit rate. So if you increase the bit rate, you make your pulses shorter. If you make your pulses shorter, you have to increase the bandwidth. The filter. And if you increase the bandwidth, noise at the output. Sometimes this, to the lecture, sometimes just the integral from, take care, from 0 to infinity, I just mentioned this, from 0 to infinity. So this is only the right-hand side, and G of magnitude of G of F d squared dF is denoted as the so-called noise bandwidth. Why we only take a look at the right-hand side? Because in the real world, you measure this and not even, it's a technical noise power spectral density, so only a right-hand-sided spectrum. So for instance, I gave you this example, and not is Boltzmann constant times absolute temperature. This is not the system theoretic power spectral density. This is the real world power spectral density. Sometimes, you find this definition in books that you say noise bandwidth. This is just integral from 0, just the right-hand side, to infinity G squared. This is then the noise bandwidth. Then you have to insert, you have to multiply this noise bandwidth with the technical noise power spectral density in order to obtain the noise power. So with N naught, and not with N naught by 2. Understand? It's done in physics. You see, in the real noise power scales with the bit rate. But sometimes it's advantageously to use this unit energy assumption. Now we know what happens with the matched filter, and then we can discuss the so-called Hurst-Nyquist criterion in the next lecture. And you will see we don't need to reduce the duration of our pulses to the modulation interval. We can use longer pulses. Yeah. Is there any idea why? Is there an advantage? Why could we want to have longer pulses, longer than the modulation interval? Any advantage? Because then we can reduce the bandwidth. If we restrict our pulse duration to a certain interval, let's say to the bit interval in this binary case, we always have a kind of rectangular shaping in the time domain. Rectangular shaping in the time domain means the energy spectral density of these pulses, we have sinc squared. Sinc squared means a lot of power or energy in the side loops. And we don't want to have this power in the side loops, and therefore we use pulse shapes which are more bandwidth efficient. This is what we are discussing in the next lecture. So thank you, and see you in one.